In this lesson, we're going to expand on powers of exponents, and we're going to look specifically at what happens when we raise something to the zero and the negative. And the main thing to remember, rather than trying to memorize all these things as if they were like a new definition, is it all comes back to what we've been doing over and over and over again in all of these lessons on exponents is think about what it means to raise something to a power and think about the rules of exponents. So before we can raise something to a power, whether we're raising it to a zero or whether we're raising it to a negative exponent, we're going to start with b being a non-zero number. So as long as sorry, I said z, as long as b is a non-zero real number, when we raise it to a power of 0, it equals 1. And the reason why that works is from the rules of exponents. Now do note that 0 raised to 0 is not defined by this definition because the base must not equal 0. 0 raised to the power of 0 really isn't defined at all. Some people argue that it's just 0 because 0 to any power is still 0, so 0 to the 0 is still 0. But, it's one of those things that you're never going to see 0 to the 0, so there's no point in even worrying about it. But in any case, anything else is going to be 1. And the reason why is, think of it this way. If I have x to the fourth over x to the fourth, well, that means I have 4x's on top and 4x's on the bottom, and we know that we can cancel them all out, and this just equals 1. But remember, what does the rule of exponents tell us? That this is just going to equal x to the top value minus the bottom value, which is x to the 0. And that's how we get anything to the 0 equals 1. Because the power of 0 just means we had a fraction where the top power of our variable was identical to the bottom power of our variable. Thus, when we take the difference, we get a 0. And when the top and bottom powers are identical, we have the same thing over the same thing. And when we have the same thing over the same thing, it equals 1. So that's really where this comes from. So it's not some new fancy, definition or rule that we're just throwing in there. It simply comes from the rule that we already set up for shorthand of, well, when you have a top thing divided by a bottom thing, you subtract them. And there you go. So let's look at some examples, right? These are all going to be 1. 1, 1, except for this one, -1, right? Because only the 4 is being raised and the negative is still out there. Remember, this is, when we see things like this that aren't in parentheses, it's akin to saying we have -1 times this thing. So this is 1. This, of course, becomes 1 times this, so we get -4. And then finally, all of this crap is raised to 0, so that's back to 1. All right. So now we can look at b to the negative n. Again, it's not some brand new thing that we didn't know about and have to memorize that, oh, when I have something to the negative exponent, it's just 1 over that thing to the positive exponent. Yeah, sure. That's the shortcut. But why is it what it is? Well, again, if you had b to the third over b to the fifth, right? You have 3 b's up here, and you have 5 of them down here, and we know we can cancel out 3 of them, and we'd be left with 1 over b squared. But we also know that according to this rule of quotients, it should be b of the top number minus the bottom number, which is b to the -2. And ta-da! B to the -2 is the same thing as 1 over b squared. Because a negative exponent just tells us that when we had our fractions set up, there were a larger number of things on the bottom than on the top, so that when we reduced it all down, we were left with just a 1 on top, and on the bottom, we were left with the leftovers, basically the differences between the two. So that's why a -2 becomes a 1 over b squared, a -3 becomes a 1 over b cubed, and so on and so on and so forth. So yes, you can just memorize these things and know that you always just take the reciprocal, the 1 over, and take its power. But you can always think back to what it means to have, things raised to a power. So that means that if B would be like, let's say we have 3/4 to the -2. That's going to equal 4/3 squared. And I should have this, so the whole thing is the negative. Because we take 1 over 3/4. And 1 over 3/4, remember, is the reciprocal of a fraction. And the reciprocal of a fraction is flipping it. Just like this is technically b over 1. So when we flip it, it becomes 1 over b. So that's the one part that kind of messes with students' brains, is when it happens to a fraction, they forget that the whole thing flips. It just seems a little weird that way. Let's look at a few more examples. 1 over c cubed, because this is just c over 1, just like this is 5 over 1. So the reciprocal becomes 1/5. And then the whole thing is technically to the -1. But 1 to any power is just 1, which is why we get back to just that, which of course is just 1/5, right? Because we never write something to the power of 1. So same thing here, right? Instead of -3 over 1, we can think of it as -1 over 3 to the 4th, and then -1 to the 4th. Well, -1 times -1 times -1 times -1, right? That becomes 1, and then 3 to the 4th, which is 81. All right, a few more. Reciprocal, so it becomes 6 over 1 squared, which is really just 6 squared, which is 36. Again, becomes -5/3, right? The sign doesn't change, just the thing flips directions, right? It flips over. Cubed, and now a negative to an odd power is still negative, so 5 times 5 times 5, 125 with a negative. And on the bottom, 3 times 3 times 3, 27. Here's a similar example where, it feels like only the y is being raised to a power, but technically it'd be the same thing if the whole thing was. Because if you put it on a 1, it's not going to change, right? So you can let this be, which becomes y to the 5th. But you could also just go, all right, I'm just going to concentrate on this. And this is y over 1, which becomes 1 over y to the 5th, which really is just 1 over y to the 5th. But that's the bottom thing. So if we put it back into what it is, it's 1 over y to the 5th, which is really 1 divided by 1 over y to the 5th. And we have to remember that the rule is when we divide by a fraction, we're multiplying by its reciprocal, and that's why we get y to the 5th, right? So it works either way. I like this one better. But of course, if this wasn't a 1, we couldn't do this trick, right? If this was a 10, we would have to go this route. And remember that, this would be a 10, and then we'd finally have a 10, and this would be a 10. So anytime you've got something on the bottom raised to a negative exponent, hopefully you'll start to see the pattern is it just flips to the top and becomes a positive on top. So if I have, 3x squared y all over y to the -3, this really just becomes 3x squared y times y cubed, because it comes up top here as a positive, which is 3x squared y to the 4th. So you can start to think about these things as it's almost like two warring factions. You've got the numerators versus the denominators. And anybody who has a negative exponent is a traitor. They've traded sides. They no longer want to be on that team. And so they basically just flip to the other side and become part of that team. So if we have something, I'll give myself some more room. Let's say I've got 3x squared y to the -4 z cubed all over x to the -2 y to the 5th z to the -5, right? Well, we've got some traitors. These guys want to defect to the other side. These guys want to defect to the other side. And these guys want to defect to the other side. And that's basically what happens. They just change teams. So now we have 3x squared. This one comes up. We've got another x squared. This y goes away. So we've got z cubed, and then this z comes up, z to the 5th. And then on the bottom, right, this one went away, this one went away. We've got the y to the 5th, and then we've got the other traitor, right, the y to the 4th that came down. And then we can combine everything. 3x to the 4th, z to the 8th, all over y to the 9th. But we also could have just used the rules of exponents. We've got x squared over x to the negative 2. So the rule says it's the top number minus the bottom number. 2 minus a minus 2. Well, that's 2 plus 2, which is 4. Ta-da! We have y to the negative 4th minus 5, which is y to the negative 9th, which becomes 1 over y to the 9th. Ta-da! We have z cubed minus a negative 5, which is 3 plus 5, right? So it's z to the 8th. Ta-da! So it works either way, right? You can always just use the rigid rules of exponents and go with those. Or you can start to see the patterns and start to see the shortcuts and start to realize that these things just flip-flop, right? As long as it's all multiplication, we don't have any addition, subtraction to muddy the waters, then this stuff will always work out. All right, I don't know that we need to keep doing some more examples. We've seen these already. This is just 1 over 5x cubed, which is really just 1 over 125x cubed. Here, only the x is raised to the power, so it's 5 over x cubed. And then here, again, only the x is being raised to a power, but you have the negative 5 here, and then all over x cubed. So the last concept in today's lesson are the properties of integer exponents, kind of summarize everything all together. If we want to simplify expressions, we know that we can use all of the rules. We can use the rules when you're multiplying things with the same base, when you're dividing things with the same base, when you're raising something to a power to another power, and when you have negative powers. Well, we've already seen that when we have negative powers stuck in these multiplication things, they're just going to trade teams, right? They're going to defect to the other side. So we're going to get a cubed c to the 5th all over b squared. Here, well, we can combine them first if we want and get x to the negative 5th over x cubed. And then we can combine it again, right? Negative 5 minus 3 gives us x to the negative 8, which of course gives us 1 over x to the 8th. But we also could have done it with defection and said it was x squared all over x to the 7th x cubed, which is x squared over x to the 10th. And then there's two of them we can reduce top and bottom, which is 1 over x to the 8th. Right? Either way is going to work. Same thing here. We can combine first if we want and just get z squared. Combine these two, a negative 4th and a positive 4th gives us w to the 0, and w to the 0 is just 1, so that goes away. C to the negative 8. And then again, use the power 2 minus the bottom. So it's 2 minus a negative 8, which is 2 plus 8, and we just get z to the 10th. And then two more. Everything raised to the negative 3. So negative 4 is to the negative 3. A is to the negative 3. And B is to the negative, well, B is to the negative 2 is to the negative 3. All right. Well, that means all of these become 1 over, right? It's 1 over negative 4 cubed times 1 over a cubed times 1 over b to the negative 2 cubed. Well, negative 4 cubed is negative 4 times negative 4 times negative 4. I think that's 96. No, 64. 64. So this is 1 over 64 times 1 over a cubed times, well, power to a power, 1 over b to the negative 6. But, oh, crap, we got a negative in the bottom of fraction, right, which becomes 1 over 1 over, which just becomes 1 over 64a cubed. We can put these two together because 1 times 1 and this times this. And then this one, remember, if we got a negative, it pops up here. Just b to the 6th over 1. And so the whole thing is b to the 6th over 64a cubed. Whew! A lot of junk to do that. Now, it might be a lot easier to think of this as just one big old blob, right? Because it's all stuck in parentheses, so it's one big old blob. So we could have just said, how about 1 over negative 4 ab to the negative 2 cubed, right? Because if we flip this, then it becomes a positive 3. Now we could do everything on it and cube this. So we've got 1 over negative 64. I forgot the negative, damn it, because it was a power of 3. A cubed b to the negative 6. And then remember, okay, well, this one defects to the other side, and it gets us right back to there. Another way that you could kind of simplify this, make it easier, is combine these two and just make it b to the 6th. And then instead of this, it's just b to the 6th, right? This is just b to the 6th, and then you have b to the 6th on top. It's a lot easier kind of conceptually to go from there to there. Much better way. All right, our last example works with actual numbers instead of variables, but it's all still the same, right? 2 to the negative 1/2 is just 1 over 2 to the 1, which is 2, plus, well, this is just 1/3. And then, of course, anything raised to 0 is a 1. Now we've got to add fractions, which means we've got to do a common denominator. So multiply this one by 3 over 3 and this one by 2 over 2 to get 3/6 plus 2/6 gives us 5/6 plus 1. So we could either leave it as 1 and 5/6 if we're allowed to have mixed numbers, or we could make this 6 over 6 plus 5 over 6, which gives us 11 over 6. Okay, that's all I got for you.